Well, welcome. You can leave it there.
Okay.
Welcome to the Friday Transportation Seminar, and I'm very pleased to introduce Dr. Roger Lindgren from the Oregon Institute of Technology. Roger received his PhD here at PSU last year, and he's an associate professor at OIT in Klamath Falls, and also he's the OIT representative on the executive committee of our new Center for Transportation Studies. So Roger's going to be presenting his dissertation research about analysis of freeway dynamics on a German Autobahn. Welcome, Roger.
All right. Thank you very much. It's always a pleasure to be here. On the drive up from Klamath Falls this morning, I sort of reminded myself I was glad that I wasn't a student anymore and having to do this once a week. But it's a pleasure to be at Portland State, and this is the first time I've seen this classroom from the podium side. I've seen it through the web, watching it down at Klamath Falls, so it's an honor to be here for the seminar series. You were talking about putting bicycles or something a little jazzier in the title, and we're joking about the somewhat mundaneness of traffic engineering, how some people view the field to be quite boring. I kind of view it as exciting, and so when I see a traffic jam, I get excited. I'm kind of a weird guy, but what we're going to talk about today is some of my dissertation research, and in particular looking at some research that was done on German Autobahn. We've all been stuck in traffic jams, and I guess I found it more exciting once I started studying traffic jams to think about what was going on around me. So some of the things I'll talk about today, some of the graphs and different pictures that I'll show will actually be things that you can observe in traffic as you're driving through it. So I think the fun thing about civil engineering, why I was attracted to it, is it tends to be tangible type stuff. So traffic and traffic jams are definitely tangible. What I'd like to do this morning is describe to you the data set. It's a very interesting data set that I was working with. I'd like to talk to you about bottlenecks within congested traffic, look at some traffic jams, and in particular, some very long and long-lasting and long in length traffic jams and queues that were built up on a German freeway that I studied. I'd like to look at some measures of queue discharge features. I'd also like to get into some discussions of what causes traffic jams. It's one thing to study them and to think it's neat to see the data showing the traffic jam, but the whole idea is, are there things that are triggering traffic jams? Are there bottlenecks being activated for predictable reasons? Because ultimately, traffic managers would want to be able to manage the flow in the traffic. And if there's certain things that they can do, whether it's with variable message signs or variable speed limits, other information that can come to the driver that could mitigate some of the impacts of these bottleneck activations. And then I'd like to talk a little bit about implications and what the implications of this research are and what I think some areas that are really ripe for further research are. The data set that I was working with, as I mentioned, is from Germany. You'll see on the map, Frankfurt is in the bottom of the map there, and the A5 that I'm going to be discussing is highlighted in yellow, studying a portion just north and west of the city. And if you've ever been to Frankfurt, the airport is just right down here. I think Schweinheim is the name of the airport area. Had a chance to visit there last summer and noticed that this was, and in speaking with the drivers there, not only is this a very heavily traveled urban freeway in the sense of a lot of commuters and other traffic, but it's also a major north-south corridor throughout Germany and the Hessen province. So the data set, about 30 kilometers in length. It's going from the south up to the north from A648, which is a Autobahn connector into Frankfurt, up to the north to a small town called Friedberg. There's a series of 30 detector stations on the freeway, and the middle kind of strip map there shows these detector stations. And the stationing ranges, the distance between the station ranges from about 400 meters up to 2,000 meters in the more less traveled sections. It's primarily a 3-lane facility, although there are some extra lanes near some of the interchanges down south there you'll see right around the Metro Frankfurt area. So in each lane, there's a series of 2 inductive loop detectors, and those inductive loop detectors are gathering data, and the data is accumulated on roadside computers. It's being put into 1-minute bins. So every 1 minute, the data is being tallied. We get count and we get speed. And we also get the vehicles being sorted into 2 different bins depending on their length. If they're longer vehicles, they're being coded as trucks, and shorter vehicles are being coded as cars. Now, of course, a car pulling a trailer will probably show up as a truck on the data, but that's not too bad because an RV or something like that is probably exhibiting characteristics more truck-like than car-like. There was no fixed auto speed limit on the A5 during the data days that I'm talking about here. And first thing that a lot of people ask me, particularly my young undergraduate students, is how fast were people going? And I found that people were traveling extremely fast in the wee hours of the morning and night. So lots of 250 kilometer per hour plus type observations seen in the wee hours. But when you really got into the congested period, you didn't see those astronomical speeds, by American standards. But you did see some 180, 200 kilometer type traffic. There are just some newly installed variable speed limit signs on the A5. And in speaking with actually my cab driver in Frankfurt, who became a fountain of information on the highway, tells me that they're not operating too often, and he'd been told by his nephew, who worked for the Department of Transportation there, that they were still experimenting with some of the algorithms and how they were going to adjust those variable speed limits. But when I was doing the data that I had was when there was no fixed speed limits for cars. Trucks is another thing entirely. In Germany, throughout Germany on the Autobahn system, trucks are required by law to travel in the right lane and travel at 80 kilometers per hour by law, but not by practice. The data that I'll show you says that they're not traveling exclusively in the right-hand lane, and they are making lots of forays out into the mid and left lanes. In fact, that might be causing a series of these bottleneck activations. And my taxi driver, again, was feeding me a bunch of good information, said that notoriously trucks, particularly since the EU has expanded its borders and how Germany is getting a lot more international truck traffic, that there's more and more violations of that trucks to the right rule. And then I think it's worth mentioning that in Germany in 2001, when these data were collected, as well as today, there's very little in the way of ramp metering. There are no ramp meters, at least there weren't in September on this highway, and I didn't hear of any plans to be installing them anytime soon. So no ramp metering on those freeway interchanges. This just shows the strip map, a little bit different orientation because I wanted to show you a little bit of the profile. This isn't dramatic topography, but in the direction of travel, which is the northbound direction I was studying, there is kind of a long, steady uphill grade. And you'll notice that just ahead of station D23, there is about a 3.5% grade there, and that certainly has the potential to start impacting truck traffic, not so much automobile traffic. Looking back a little bit at what's been done in freeway studies in the past, there's really a wealth of good, solid studies that have been conducted previously. I would say going back at least 50 years, of people analyzing freeway bottlenecks. And I think of that 50 years as being that's about as long as freeways have existed. So I think as long as we've had freeways, we've had congestion problems, and we've had, to a certain extent, some bottlenecks. A lot of the data from early studies were limited by the collection techniques. They were manually collected, either going out and doing direct observation, maybe analyzing air photographs, which is great data, but it's really hard to collect large quantities of it to get the sort of breadth and depth research that we're looking for. So you had short durations, you had studies that were occurring at fixed points that were very interesting, but it maybe wasn't getting the full picture unless you can look at a larger strip of the roadway and look over a longer time period. And then I believe that something that was limiting some of these previous studies was the lack of good bottleneck activation criteria. There were bottlenecks on the freeway, that is, places where the flow was restricted, but not all bottlenecks are activated. In other words, in the middle of the night, when you're going past an interchange, doesn't matter whether there's a lane drop or a merge or diverge. If there's very little traffic there, the bottleneck's not activated. So you really have to be careful when you're analyzing traffic data that you look for activation. There have been a number of good studies more recently on Canadian, British, US, and now German freeways that have been using some better analysis methods, more robust, and these are now being applied in this study and on some good work that's being done right now here at Portland State by the ITS lab on German freeways using these data analysis techniques. If you look in the literature, you'll find that a number of previous studies were using variables like I'm showing here on the screen. Velocities and flows, so the top is velocities in 3 different lanes. So the black is the left lane, the red is the middle lane, and blue is the left lane. First we've got speed in the upper one and flow in the bottom one. You can see that the plotting techniques exhibit a whole bunch of variation, and there's certainly some decreases that we see on the slides there, but it's really hard to tell whether we're seeing just statistical variations or whether there's really time-dependent changes occurring. And so what you can do with this is, go back one. What you can do is, in order to clean the data up a little bit, you can start to aggregate and take it in larger time periods. But what that does is diminishes your ability to determine exactly when certain things occurred on the roadway. So I think there was some real limits in this. Flow. Vehicles per hour in this case. So it's a rate, traffic rate. Thank you very much. I think I copied and pasted. Yeah, it should be vehicles per hour, certainly. Apologize for that. So the limitations of some of these data analyses, that you can look at these, you can certainly see drops in speed, but are you going to be able to find out exactly when the drop in speed occurred? And are you going to be able to pin it to a particular point in time and a particular place in the roadway where a bottleneck has become activated? That's the key and the objective of my research. Some of my motivation came from a body of work that is led by Boris Kerner. Mr. Kerner has published a number of papers together with several colleagues and has done a lot of analyses of German freeway data. Mr. Kerner comes from a physics background and has published a number of things in physics journals that have caused a little bit of alarm to traffic engineers because he's using some other techniques other than traditional traffic engineering analysis techniques, and what he was finding was that he was seeing what he thought to be spontaneous bottlenecks, that is, congestion occurring on the roadway for no apparent reason. And this sort of got the attention of a lot of traffic researchers, and I sort of got caught up in that getting the attention of as a young graduate student, starting to learn about these things, found out that there was some interesting work coming out of Germany. But when you started to look a little deeper, we found that there wasn't a lot of work being done on analyzing German freeway data by some techniques that have been used successfully, as I said, in the US and in Canada and on British highways. And so my research represented at the time one of the first times that German freeway data was made available to us in the US to analyze using these techniques. I want to mention that since then, several more freeway data sets have become available, and there's some work that's happening right now at PSU. I think Steve Boyce actually was in a few weeks ago to talk to the same seminar series about some A9 work, and is continuing on that. So that slide, I don't want to claim I'm the only one that's doing this type of research, but at the time it was one of the first German data sets that were made available. I put this slide up to kind of give you a framework for some of the things I'm going to talk about today. It's my color slide, so it's kind of the big showpiece. I want to explain it to you. Steve tells me that he's talked to some of you about this technique, and some of you may have used it, so if it's a repeat, please forgive me. But what we're looking at on the left-hand side is the strip map from D1 through D30, moving in the northbound direction. And then the map represents kind of a three-dimensional, if you will. We've got along the x-axis, we've got time, and I'm looking here from a period from noon to 8 in the evening. Along the y-axis, we have the stations from D1 through D30, and then, I don't know if you can see it from where you're sitting, but there's some faint gray lines that are going over to allow you to kind of trace that the stationing back over onto the map. And then the guts of the map here is really red, green, yellow. And green is good, so green means fast. And generally speaking, that means that traffic is pretty freely flowing. And then yellow, as you look at the speed variations there, ranging from 200 kilometers for very dark green through to light yellows for speeds 100 kilometers and a little bit lower. And then as we get down below 60, the yellow sort of transitions to an orange, and then for very slow traffic, we have red. And what's immediately obvious on this graph is that there are a series of things occurring on the roadway there. There are speed disturbances. And what I want to do is dig a little bit deeper and find out exactly where and when are those speed occurrences occurring, okay? And this map, while not great for doing diagnosis, is really a nice way of kind of showing things all together. So it became a wonderful summary tool, really. And in fact, in the early stages of research, what it did was give you a nice snapshot of what was going on that day. Allowed me to then start digging deeper in a particular time in a particular location and see what was happening with the traffic. I want to point out something to you. You'll see a series of these red lines moving down the graph. And what you'll find is that they're carrying back with great uniformity at almost a constant speed. And so that was of great interest to me initially, and as I got into it, I realized why they were occurring that way to a certain extent. And it just was amazing to me the regularity at which they were occurring and the fact that they were holding their speeds and the tightness of that red band through there. Like I mentioned, that slide is kind of the big picture. It shows everything together. But to really get down into the details, to really find out what was going on and when, I needed to be using a much finer analysis tool. And so I used a method that has been around for a few years and been used quite successfully. What this method is a plot of cumulative counts. If you imagine now on the x-axis we're plotting time, on the y-axis we're plotting cumulative count, number of vehicles that have passed a point X. So someone's standing there on the road counting these vehicles going by and the times that they go by. And so if you think of cumulative count, that means the total number of vehicles passed a stationary observer at one point. If you would see a change, first of all, let's define what the slope of this line is. And yeah, it's not kilometers per hour. This is flow. So this is numbers of vehicles per time. And I'm looking at it primarily in vehicles per hour. So if the slope is flow, then changes in slope represent either flow increases or flow decreases. Oh, it sounds good. And it works well on this style of graph because I just kind of made this up on Excel, okay, with some fictitious data. But when we look at data coming from the freeway, what we find is the very large number of vehicles going by here, 5,000 vehicles going by in a 1 hour period. Well, when you get that cumulative count plotted on the time series here, you'll find that, it looks like a straight line. There's a little bump there, see around 1,400, but I certainly couldn't tell a whole bunch from that, okay? So I need to zoom in, right? Need to get in there and look in a little more detail. So the way I zoomed in was to, take a straight edge and find out what is the kind of average flow that's occurring throughout this time period. So I put my straight edge on there. I find out that the time period average flow is about 4,910 vehicles per hour. And that's what that pink line represents. So if the blue line represents cumulative count, then the pink line there is kind of you could call it the background flow if you want. And then what I wanted to do was plot a smaller variable. Instead of plotting the entire n, if I plotted n minus the count at a particular time. I get the count at a particular time by taking this background flow rate of, say, 4,910, for example, multiplying it by the time that's elapsed from the beginning of the analysis period. And then what I'm really counting is just number of vehicles between the two lines. Well, when I plot the number of vehicles between the two lines but hold the y-axis the same, I get that same plot, which makes sense. But now I don't need to plot all 5,000 vehicles, right? I only need to plot up to the limit of the spread, which was about 250 vehicles in this case. So now by plotting on the x-axis time and on the y-axis the difference between those two lines, I now get a line that instead of just having a little blip around 1,400, now shows what to me was a pretty notable flow drop. So again, I get the straight edge out and I do some piecewise linear interpolation here, and I get some differing flow rates. And in particular, the one that I'm looking at that really stands out is this 5510, dropping pretty significantly here, I think, from 5510 down to 4220. So it's no longer just a little blip on the graph. Now I'm getting into detail. Find out when that flow drop occurred. Work with me for a moment. If you go back to that previous slide where we talked about the kind of standard cumulative plot at one station, I'm now calling that X1. What if I added another station and I called that X2? So now I'm getting counts at two adjacent stations. The difference between these two stations on the time axis is going to be the trip time between the two stations. And if you think of it, the free flow time that it takes for a vehicle to get from X1 to X2 in freely flowing traffic, that is, would be that reference vehicle trip time. What else can we see from this graph? Well, for example, at any particular time, say T1, the difference between these two plots would be the number of vehicles that are on the roadway between X1 and X2. And then at a particular vehicle, say vehicle J, we can see its trip time. So I said in general, we're talking about the horizontal difference being trip time, but we can actually pin it down to each individual vehicle's trip time. Okay? Now imagine that I take that upstream curve and I shift it to the right by the free flow trip time. If all the vehicles were freely flowing, then the two curves would be perfectly superimposed, right? Because each individual vehicle's trip time would simply be the free flow trip time, okay? And in the early reaches of the curve, that's shown. Those two lines are sitting one on top of one another. So what can we say? We can say that in the shifted curve analysis, then, that curves that are superimposed represent freely flowing traffic between those two stations. Now, where the curves are separated, we no longer just have time, we have the excess of time, right? So the difference between the blue and the pink lines here horizontally for a vehicle K is excess travel time. Traffic engineers, we like to call that delay. And what for time 2, what's this accumulation? It's not just the number of vehicles on the roadway, it's the number of vehicles on the roadway between X1 and X2 that's in excess of what would be there during freely flowing traffic. So we have excess accumulation and we have delay. Well, those are traditional definitions of congested traffic. We have congestion now. We have, in other words, the activation of a bottleneck. Something is being caused, or at least it's occurring at these two stations. There's something occurring. Now, whether it was activated further upstream or downstream, we don't know yet. We're just looking at two different stations that are adjacent to one another, of course. Think to the traditional definition of a freeway bottleneck. It's just a point on the road, downstream of which the traffic is flowing freely. It's unqueued, and upstream of which the traffic is queued. So that's the fundamental definition of a bottleneck, and you can see that by taking that analysis technique that I showed in that previous slide, applying it to longer time periods and to multiple stations, that we can start to find out when and where freely flowing traffic existed or didn't exist. So that's what I'm going to do next. I'm going to show you how that those lines that were just created to show you the basic idea have now been applied to some real data. So the real situation I'm looking at here on the A5 is an interchange to the north side. It's going off into a smaller town called Friedberg. You notice that station D24 is immediately upstream of the off-ramp. And then I've got data here for 24, 23, 22, 21, and 20. So D24 I've plotted in black, and I've got the difference in cumulative count plotted on the y-axis, time on the right. And then what I've done is plotted stations D23, 22, 21, and 20, and I've shifted each of those over by that free flow travel time. Now, it's not quite as clean as it was on my hypothetical drawing. Not all these lines are perfectly superimposed because, yes, there's a little bit of variation going on just in the traffic. For one thing, the traffic detectors aren't necessarily catching each and every vehicle. There's a little bit of detector error. People change lanes right as they're going over a detector, those sorts of things. But you can see that there's clearly a trend here. We're seeing that these stations 20 all the way through 24 for the early reaches, you know, almost until about 1400 there, those lines are pretty much superimposed, okay? Really looks like freely flowing traffic. If you see what's happening at station at 1401, at station D22, what you'll see is that we see a distinct change now in the behavior of the graphs. Curves 23 and 24 remain superimposed. So there's freely flowing traffic throughout the time period now, including past 1400 between stations D23 and D24. But upstream of that, we're starting to see separation vertically and horizontally, excess travel time and excess accumulation. So there's congestion. And we can see that at about 1401, that seemed to be where the spread was starting to occur between stations D22 and D23. And then at station D22, we see a drop in flow. Well, why would there be a drop in flow? It's because we have a shock moving back through the traffic stream, and the drop in flow is now hitting station D22, upstream of this occurrence. So downstream of D23 and stations D23 and D24 have freely flowing traffic. We say that those are downstream of the bottleneck. Stations D22 and D23 have excess accumulation and delay, and so we say that that's upstream of the bottleneck. So it's somewhere between D22 and D23. And with the data that I had, I can't get any more detailed than that. I don't know exactly where between those two stations, but I do know that it's occurring between those two stations. And then I can see that flow drop here with magnitudes, and I can also see how that flow drop may have also been associated with a drop in velocity. So what I'm showing in the inset here is a graph that's created in a similar way to the cumulative count curves. Sounds a little strange, but we're actually accumulating velocities here, and then doing the same differential with some type of a background velocity. So what I'm really trying to do is zero in on key changes in speed. I was somewhat critical of some of the past work that was done where you're just looking at scatter graphs of speed because the speed's going up and down, hard to tell exactly where those variations are occurring. Here I can get really detailed and see where the variations are occurring. At 1402 here, we have a drop from 95 kilometers per hour to 45 kilometers per hour. Pretty dramatic drop. And when's it occurring? It's occurring at that same time when we had the flow drop. So it's really a verification of when that bottleneck was activated. As we look further upstream, we'll see that those flow drops reach further upstream stations at intervals. Say 1404, the flow drops at station D21, verified by a drop in speed. And then at 1407, a flow drop at station D20, again verified by a drop in speed. I mentioned to you at the beginning that the data were coming to me in each lane and then individually by truck and car. And what I'm showing here is that we can trace how that velocity drop occurred on a lane-by-lane basis to try to get an indication, was it occurring earlier in one lane, later in another lane? Was this pretty uniform? It's pretty uniform here. You'll notice that the right lane drops just a little bit later, but it looks pretty clear that the left and mid lanes are dropping right at that about 1402 time, say for station D22, which was that first speed curve that I showed you. And then what I could also do is look at individual cars and trucks. I haven't shown that graph here as well, but they are things that I analyzed to look at how the vehicles were being impacted on the roadway and trying to see whether there's any discernible differences between car and truck behavior. This shows the rest of the speed curves. But now we're looking downstream. Why would there be velocity drops downstream of the bottleneck? At first blush, that doesn't seem to make sense because it's downstream of the bottleneck. But if the cars have had to slow to move through the bottleneck, okay, now imagine that they are accelerating out of the bottleneck or away from the bottleneck, but they're not going to instantly get up to their free flow speeds. And these German drivers are driving quickly, so for them to get back up to their free flow speeds may take a little while. And so we will see in station D23, which is just the first station downstream of the bottleneck activation, that is actually having occurrence. And this, when I first saw this data, I thought something was wrong, and I went to Rob Bertini and said, help me figure out why is the speed dropping earlier at station D23 and D22. So as Rob does on the great whiteboard there at the ITS lab, he drew me some pictures, and we got the idea that the backward moving wave is not moving at the same speed as the forward moving shock, right? The shock of increasing speed is moving at the speed of the vehicles. And so they might be moving much more quickly down, so the shock moving downstream, okay, is moving more quickly than the shock that's moving upstream. And so that's why this drop at station D23 is occurring just slightly before we saw the speed drop back at station D22. Does that mean that the bottleneck's closer to D23? Not necessarily, because the speed of the wave is also faster. So you could do kind of a triangulation and try to figure out where that occurred between those two stations. And then station D24, the effect is much milder here. I show it just because I want to show that there are some impacts, and the impacts are there, but not nearly as notable, just from 96 to 92. So you're just seeing the remnants. And by the time I got to the next station, I actually had merging traffic, and by then any remnants of the bottleneck there seemed to have disappeared from the speed curves. So that was a long way of saying to you that I could find out when something happened. Okay, so I was looking for when and where something happened. So I could go back to my color picture and say, here is the activation of a bottleneck. I call it C1 because it was the first bottleneck I found on day C. And I found that it was activated at 1402 and that it was occurring between stations D22 and D23. So this graph that I said gave me a nice snapshot also becomes a great way of summarizing some of the results that I'm getting. Once it's activated, I want to know how long it's activated. And what I did for that was look at, well, how long were those curves separated? When the curves come back together again, that's freely flowing traffic. I want to know that as well. Very important to know the confines, the temporal limits of this bottleneck. Okay, I've now got some of the spatial data of where it occurred, when it started. Now I want to know when it is deactivated. So what I'm looking for here is the time when the curve for station D22 becomes superimposed once again with the curves from D23 and D24. And in this summary, in order to show it all to you, it's kind of hard to see exactly where the red and the blue line come back together. I used some much smaller scale maps to zoom in on to figure this out. But between speed increases and the curves coming back together, I was able to determine that at 1417 that we had an end of that bottleneck activation between 22 and 23. Now, there's still queued traffic further upstream, and it's going to take a while for all the effects of that queued traffic to dissipate. And so I can look further upstream. Before I do that, I just want to see that I can verify that when the curves came back together, I should see an increase in speed, right? Because freely flowing traffic, the bottleneck's dissipated between 22 and 23. So now it's free flowing at station 23. It's free flowing at station 22 at the point where the curves come back and the speed increases. So I see speed increasing at about 1417 here. So now I've got bottleneck activation, bottleneck deactivation. I've defined the limits. And remember, I mentioned that red line moving back through the traffic stream. This is the shock speed. This is, you're driving down the road. This is everyone putting on their brake lights. That's the speed of that shock. If people were all reacting at the same time, we would see the brake lights coming on in progression, and that's the speed of that shock moving back through traffic. It was a speed of approximately 21 kilometers per hour. And notice how close that line, if we took that slope, 21 kilometers per hour, and compared it to all the other shocks, they all seem to be behaving the same way. So I'm an engineer. I get excited about straight lines, for one thing, and the fact that repetitive straight lines, it's all occurring at the same time. And to me, that was pretty novel. And so again, I went to my colleagues at the ITS lab and said, what else has been done? Do some more reading, find out, yeah, other shocks have been measured. And in fact, this is not an unreasonable speed. This type of speed had been seen on a number of different roadways. I'm not saying it's the exact same on every freeway, but there seemed to be some reproducibility of that. So I repeat that analysis many more times, okay? I plot so much paper that it fills up 2 filing cabinets in my office now. But I use all these subplots that I've showed you, the shifted and oblique plotting, to find out that there are a whole bunch of bottleneck activations on that day. And they range from, very short in duration and very limited impact on the road to some ones that had some pretty serious impact, long-lasting. Imagine this shock. I mean, that's moving C1, that's moving back through over 20 kilometers worth of traffic, which seemed quite amazing to me. Some of them, like I say, like C19 there and C20, much shorter time periods. Notice how they tend to be grouped around obvious locations on the highway, around areas where traffic is diverging or traffic is merging. And so there were a total of 20 on that day, and then analyzed another 6 days of data as well. In the total dissertation, I believe that it was, we had about 85 different bottleneck activations. Okay, once the spatial and temporal limits of the bottleneck activation have been established, I know when and where, right, for how long. Then I can start to look at what's, so what is kind of the question. So why look at this stuff? Well, I told you that I wanted to look at what might have caused them, but I also want to look at the impact of the bottleneck itself. And so if I look at the flow diagram, and I'm just repeating some data here, but just showing it to you in a slightly different way. I'm now showing you the cumulative flow curve, the oblique cumulative flow curve for station D23. This is the first station downstream of that bottleneck that I showed the activation of. And I've shown some dashed lines here that represent the activation and the deactivation times. And the red arrow there is saying, hey, there's a pretty notable decrease in flow. Should we expect that? Well, I think maybe we should, because the capacity of the bottleneck is not necessarily the same after it's been activated. So the pre-bottleneck activation flow here of 5,190 and 3 lanes, that seems a little lower than what I was thinking of. I looked in the German highway capacity manual and found out that, yeah, actually that was not out of line with some of the things that German engineers would be saying would be the expected capacity of a 3-lane facility like that. But then after the bottleneck is activated, drops, you can see 15.4% for that first straight line, and then over the life of this bottleneck activation, the total drop was a little bit less than 11%. So I think that's pretty significant, because what that's saying is that there's really 2 capacities, that there's a capacity before activation and after activation. Well, freeway managers take note, right? Because this is very important. This means that you're losing, possibly here, just in this one case here, you're losing 10%. That if you could keep that bottleneck from activating, you could be getting a whole bunch more vehicles through per hour, right? So is it important that there's 2 capacities? Yeah, I really think it is important. Another way of showing the speed data is to show it in relation to the flow data. So what I've done is added speed data now to the flow curve, and then you're going to see these drops in speed when the bottleneck was activated, and then increase in speed when the bottleneck was deactivated. But I want to show this curve for one other reason, and that is an important thing that I'm looking for is to find out whether there were any abrupt changes in the speed between station, in this case at station D23, because I want to make sure that I haven't got caught up in the effects of a downstream bottleneck and its queue spilling back and impacting my location. So because I don't see any abrupt changes in speed here associated with the flow changes, I can be assured that I'm in a situation where it hasn't been deactivated now by having a backward flowing queue through my station. Just an example of some of the data and how I reported some of the results. I looked at this bottleneck C1, as I showed you. It was active 1402 to 1417. And here's the outflow. I looked at it on a lane-by-lane basis, and then also all lanes together there. So you can see how the left lane carrying majority of the traffic while the bottleneck was active, 1,800, 1,600, and about just a little less than 1,200. Well, it turns out that in the 6 days that I analyzed in my research, that a bottleneck occurred between stations D22 and D24, and I grouped those together because I felt that they were being influenced by the same exit just about downstream of station D24. So I called that range of about, I think about 1,200 meters between D22 and D24 as kind of one analysis area, and found out that 21 times, so pretty repeatable, that this bottleneck is being activated. The durations ranged from really short, 7 minutes, up to 223 minutes. So there was a couple of really long activations there. And it was interesting to note that in those 21 times, I had average flows that were reasonably close. 4,890 is the average flow. You can see the standard deviation there. The left, mid, and right lane flows are shown as well. 12 of those 21 were of particular interest to me because they were bottleneck activations that occurred when the previous traffic flow was free flow, uninterrupted flow, okay? And so if we've got freely flowing traffic occurring prior to the bottleneck being activated, I tried to differentiate those from bottlenecks that were being activated but were being activated and were being impacted by the flows from downstream bottlenecks. Okay, if the flow was being choked off downstream, then I had a hard time really taking that data and analyzing it explicitly for mine, right? So I wanted to be looking at bottlenecks that were kind of isolated, not being impacted by downstream bottlenecks. So I called these isolated bottleneck activations. So 12 of those 21 were isolated bottleneck activations. In particular, what I was interested here is whether that drop in flow that I saw in this apparent two capacity thing, did that occur at more than one place? Was it repeatable? Was it reproducible? So here we've got on both all lanes and on a lane-by-lane basis, the pre-queue and the discharge flows, and then the associated drops. I think what was interesting here is that the overall flow drop was a little over 4%, but a large amount of flow drop was occurring in the left-hand lane, the faster flowing, automobile-dominated traffic. In the mid lane, a much less pronounced flow drop, and then in the right lane, almost an imperceptible flow drop across the 12 stations. So in the right lane, where it's pretty much truck-dominated, we weren't seeing a big decrease in flow after the activation of the bottleneck. Now, it's important to know what's going on downstream, what's happening at the outflow side, the outlet, right? And I mentioned to you why that's important for a freeway manager to know what is the real capacity of my section of freeway. And more than just looking at a book, is there a way of actually determining with real data what the capacity of that section of freeway is? But also it's important to look at what's going on upstream and what might be happening in the traffic flow that has the potential to trigger a bottleneck activation. And so I looked at a large number of different things here. I looked at lane changing, and I looked at trucks and cars and things like that. And I want to show you just a few of the slides that led me to some conclusions related to bottleneck activations. Here is a slide showing truck flow. This is, again, oblique curves, but I've filtered out the cars. I'm just looking at trucks. So I'm looking at trucks, and the numbers there represent a certain number of trucks per hour. So in the left-hand lane, pretty long, steady stretch there with an average of about 60 trucks per hour. Well, that's really about a truck per minute. Remember, they're not supposed to be in the left lane at all, right, by German law, but they're there. And they're there at station D22. Remember that that's on an uphill grade, and it's just ahead of an interchange. So those two things are kind of conspiring to make us think that maybe the truck shouldn't be there, and what happens if more trucks move over there? Well, look at that 2-minute period where there's 5 trucks going in a 2-minute period. That equates to 150 trucks on an hourly basis. Pretty sharp increase there. And that's happening just ahead of the bottleneck activation time. The mid lane, more trucks are using the mid lane, but again, there's a pretty sharp increase from 40 to 180 on a per hour basis. And then also in the right lane, this is where majority of the trucks are, right? But still, we see a flow rate of 360 trucks per hour, and then that's increasing 144% to 880 trucks per hour. That's 30 trucks in a 2-minute period just prior to the bottleneck being activated. Okay, so lots of trucks, and when I drove the freeway, I could get a sense of this. The trucks stack up. Some of the trucks are slower, so they'll be controlling the speed of that truck platoon, if you will, moving up the hill. A few trucks want to go past, right? They want to get around. They're impatient. And if a few of them go around, that doesn't seem too bad. But if a few of them start to go around right at the time where the rest of the traffic seems to be building up, now you've got a truck that's maybe at 80 moving over into the mid lane where cars were wanting to move at 130 kilometers per hour. You can see the impact that would have. Okay? And so trucks moving out of that left lane into the moving out of the right lane into the mid and left lane seem to be causing some of this, the triggering of the bottleneck activation. I want to look at bottleneck inflow again, but now on an all-vehicle basis. And what I'm doing here is looking at the left, mid, and right. I've parsed it out by lane. And I want to look at just the 2-minute band. See that little gray area there on the graph? That's showing the 2-minute period just ahead of the bottleneck activation. Look at the left-hand lane, 2,430 vehicles on an hourly basis in that 2-minute period. That's a pretty significant flow. 2,230 in the mid lane, 1,230 in the right, quite a bit lower, but remember that those are long vehicles because, as we saw in the previous slide, a very large percentage of them are trucks. In addition, there was this idea of the trucks and their influence on the traffic stream. And one of the things that I looked at, and there's always a concern that highway engineers have, how do we track the influence of a truck on a traffic stream? What we often try to do is make them equivalent to a certain number of cars, and then we replace it in the equation. It's kind of a standard thing that's done. Highway Capacity Manual has some guidance on that, what sort of passenger rate to use, passenger car equivalent rate to use. And so what I did here was, because these weren't severe grades, I chose a value of 2 passenger cars for every truck. And then I wanted to look at equivalent flow. So this is equivalent if we take all the trucks, turn them into 2 passenger cars, add them up with the passenger cars, what's the flow rate? And that's what's shown on the bar graph here. See the big spike there, 3,060 equivalent vehicles per hour in that 1-minute period just ahead of the bottleneck activation. So further indication of trucks and their influence in the activation. What else did I look at? Well, obviously I was concerned with the off-ramp, so I looked at the off-ramp, I looked at the trucks, I looked at high flow rates in all lanes, and then in that right lane in particular with the truck influence. This is just a little graphic that shows you on a number of these isolated bottleneck activations, how many of them seem to have reproducible triggers. You'll see that the high pre-queue flows in all lanes, all the bottleneck activations seem to have that surge in traffic, okay, and they coincided with a surge in truck traffic. So it's when an increase in truck traffic coincides with an increase in overall traffic. And then in several of them there, in 7 cases, there was also a notable increase in the off-ramp. And so there was off-ramp demand. Maybe it's some vehicles moving over from the left lane moving their way over to the right lane in order to exit. Of course, they've got a pretty steady stream of trucks there. It's not the easiest thing to get into that lane. So there's another issue that comes into play with bottleneck activations. The deactivations were not quite as voluminous. I didn't have as much data as I would have liked here on the isolated bottleneck deactivations. And so I'm going to show you a couple things that seem to be reproducible, but to say something's reproducible over 2 activations is not a real strong statement. And I'm continuing work in this area and work with others to try to get more data on these bottleneck deactivations. But as you might expect, it seemed as though when we had a drop in off-ramp flow, so there's less demand at the off-ramp, that seemed to coincide with it. It happened in both the 2 cases that I analyzed. And also, we saw a drop in right lane flow, in particular in trucks. So the truck rate drops off, less demand for the off-ramp. That seemed to signal the end. And here's just an idea of how I would express that graphically. I can see the off-ramp flow dropping there, 31% at the time of a deactivation of a particular isolated deactivation, and then a drop in truck flow happening just ahead of the deactivation, which makes intuitive sense to us. Also looked at merges. I'll spare you the details of all the graphs, but I did the same thing for merges. Looked at areas where vehicles were merging onto the highway. I found that a merge bottleneck arose upstream on the roadway between D7 and D8. You'll see there the red and the blue stations. 12 times that bottleneck area had an activation. 7 to 73 minutes, again, pretty widespread. And here's some indication of the average flows, both on an all-lane basis and then left, mid, and right. What happens on merge? Do they experience the same sort of 2-capacity phenomena that Diverge did? Yes, according to my results, yes, they did. Not maybe as large in magnitude, a drop of a little bit more like 2.5%. But now notice where the majority of that drop is coming from. It's the mid lane, quite a bit different than the Diverge, which was left. And now notice that the right lane does experience a flow drop. Of course, the right lane is the area that's having the most friction between the merging traffic and the diverging traffic. And also, the mid lane, that's what's receiving the lane changes, right? I noticed that the German drivers are actually quite polite in a way. Not if you're traveling slow in the left lane, because they flash your lights at you, but they're pretty good at interchanges, and I find, in a way, kinder than some American freeway drivers are, where they would let you merge over to allow for incoming traffic. So people in the right lane were pretty good at making gaps for the incoming traffic, but then the mid lane people were allowing people to make lane changes over, which was nice, and sort of kind of a polite driver technique. And that kind of showed up in the data here, though, because polite drivers are going to cause a decrease in capacity, right? So decrease in flow rate in those mid lanes. Triggers for the merge activations. No surprise here. On-ramp surges. More vehicles trying to get on the road, causing those merge activations. And then we've got the net lane changes, as I just talked about. The people are moving over into the mid and left lanes, but they're not traveling as fast as the people in those lanes had wanted them to travel. So that seems to be what's causing it. Cause and effect there. I'm not saying one might be effect of the other. It's primarily this on-ramp surge in flow. Here's the on-ramp flow here, the D6 on-ramp. And here is an idea of vehicles making a movement towards the right, mid, or left lanes. A positive slope is indicating in this graph movement into the lane, a negative slope, movement out of the lane. Where are they coming from? They're coming from the right lane, right? Right after activation there. Where are these vehicles going? They're going to the mid lane, and you'll notice going over to that left lane, there's a pretty interesting one there. 10 vehicles per minute net lane change behavior over to the left. So in conclusions, or some of my conclusions were that bottlenecks were occurring at predictable locations, merge and diverge areas predominantly. That the discharge flows are reproducible across all the lanes and pretty much on a lane-by-lane basis. that the discharge flows were nearly constant, and so therefore I think they should be viewed as the bottleneck's capacity. So when the traffic engineers are analyzing these pieces of roadway, I think they need to use this type of technique to find out what is the capacity of that section of freeway. And I'm not claiming to be the first person that saw this to capacity. James Banks from San Diego has published papers on this, and I think this was some independent validation. I don't think it had ever really been done on the German freeways prior to me doing it, so I was able to validate Banks's to-capacity theory. And so we have discharge flows were lower than the pre-activation flows. Pretty important from a freeway management point of view. These traffic disturbances were traveling at nearly constant speeds. I mentioned just about 20 kilometers per hour, and they were traveling very long distances, 20 kilometers. When I say without spreading there, I mean you didn't see the red bands getting larger. In other words, the amount of time that congestion was evident at each station remained almost uniform, okay? Almost strangely so, in my opinion. I couldn't believe quite how tight those red bands were. Merge bottleneck triggers were increased on-ramp flows and lane changing to the left. Diverge, as I showed you first, were off-ramp flows, high pre-queue flows, and truck influence in the right lane. I think I benefited greatly by having data that was provided to me in the way it was, nicely split up in cars and trucks. And it allowed me to do some things that, quite honestly, you can't do from all loop detector data, because not all loop detector data is parsed in that way. So I think it allowed me to do some interesting things and to start talking about truck influences for the bottleneck activations that maybe there hadn't been too much of before. I think that one of the things that I need to do in some of my further research is to look to the data that I've collected here and look at some of these results and start looking at both macroscopic and microscopic models of that freeway, because ultimately people want to be able to come up with models so they can predict some things without real traffic. Well, I think that the type of data that I've collected would be great for calibration and validation of those models. And then this third bullet here is something that's being worked on right now. Steve and Robertini are working on the variable speed limits on the A9 and seeing how those variable speed limit signs would affect bottleneck formation. And then variable message signs and other ways of communicating information to the driver, I think, also need to be evaluated. I'd like to thank Dr. Robert Bertini and all the ITS lab team, kind of past and present. Many of you I've just gotten to know recently, but I worked with the previous group of people, graduate students, as we went through. I really valued the opportunity that I had to bounce ideas off of other people. My good friends Monica and Suti, in particular, were of great assistance when I was doing this research. And most of you, or a lot of you here, are graduate students, I know, and I think it's just really important to build that collaborative effort and to be able to speak with your peers and discuss things. And there's always a great team atmosphere that Chris and Rob have maintained in the ITS lab. Very grateful of that. The Hessian National Office for Road and Traffic, they're the ones that provided a lot of the raw data. And then I had some wonderful collaboration with the Institute for Economics and Traffic at Technical University Dresden. Martin Schoenhoff and Dirk Helbing provided a lot of the preliminary data analysis, and we were able to keep in touch with them. I would always have little questions about German to English translations, and my dictionary wouldn't have traffic terms in it, so I was able to lean heavily on those guys at Dresden to be able to help me out with some of the analysis. I'd like to thank the department, Civil Environmental Engineering at PSU, and also my home department, Civil Engineering and Geomatics at Oregon Institute of Technology. Both those departments provided support for me while this research was being conducted. Oh, I already have that one on there. Sorry, I'm going the wrong direction. All right. So, any questions or comments? Okay, certainly.
So diverge bottleneck cases, you mentioned that you observed increase in off-ramp flows.
Yes.
Did you also observe systematic lane changes to the right lane?
So the question is, in the diverge bottlenecks, looking at increases in off-ramp flow and then lane changes to the left. And yes, lane changes to the right associated with it. There were two things going on, and I guess the quick answer is yes, but all you can really get from the loop detector data is net lane changing. And I believe that what I was seeing in the data was a combination of some lane changing to the right with people wanting to make the off-ramp move, but that was being masked by people moving to the left to pass the climbing trucks on that uphill grade. And so you kind of had a net sometimes of 0 where you really felt as though there should have been more vehicles moving over. They had to be coming from somewhere to make the increase in the off-ramp flow. And so the nature of the data didn't allow for a real crisp determination of that lane changing. But I think there's definitely more work that needs to be done in that area. Sure.
I'm interested, having studied German freeways, is there a noticeable difference in freeway dynamics, would you say, as a result of driver behavior differences and cultural factors between, say, North America and German freeways?
Okay, to repeat the question, we're talking about driver behavior differences and cultural differences maybe between German or European freeway analyses and American. You know, I guess the first one is they drive fast, right? So just because of the nature of the no automobile speed limits on that section. I believe, and some of this is kind of subjective, okay, but having studied both some American freeways as well as some German freeways, I felt that the Germans seemed to be more rule-oriented. In other words, if the sign said exit, you know, for this exit, change lanes or whatever, they'd move over there, okay? You would have more defined movement like that, a little bit less chaotic maybe than an American freeway. And then in driving on German freeways and some Austrian freeways as well this past summer, that sense that I got from the data about the rules-oriented driver behavior was really kind of validated in my own mind. So yeah, I think there are some differences, but yet in the same way, it was interesting to see how many of the same things are present in both. The two-capacity theory, the whole idea of with the lane changing and the merging and diverging and that type of thing. So similarities and some differences, though.
I'm not sure I understood the particular point. You said there's different rates of travel for the bottleneck activation heading backwards versus the deactivation that goes backwards?
The different, I think we're talking about the speeds at which the shock was moving. Is that the idea? Yeah. So the question is the differences in shocks between upstream and downstream. Is that okay? So when the shock is moving upstream, okay, it's moving back from the point at which the bottleneck has occurred. You noticed on the graph there, I said that it was moving at about 21 kilometers per hour. That's that speed of vehicles having to slow down, right? So it's the speed that connected the flow drops and the speed drops at each of those stations. On the downstream side, that shock is a recovery speed wave, and it's moving downstream at the speed that those departing vehicles are moving, accelerating away from the bottleneck point. That's moving downstream, yes. And so what you've got, remember I showed you stations D22, or D23 downstream. It's just downstream. There's still a drop in speed. It's not quite as noticeable because if you're standing on the roadway and you're standing just downstream from where a bottleneck is occurring, imagine, a classic one is one lane is blocked off for construction, so people are squeezing through. And then the minute they get through that, what are they doing? They're speeding back up to what they would want to travel at their free flow speed. Okay? So there's still, in that case, at that first downstream station, there was still a noticeable drop in speed, okay? And it had occurred sometime after the bottleneck had become activated, okay? But then by the time you got to the next station and the next station downstream, the impacts of that were lost. So that shock is moving downstream at the speed of the departing vehicles, discharging vehicles.
And it dissipates sooner, distance-wise.
Yes, it does, because they're accelerating and they're moving. Let's say in the German case, 80, 90, 100 kilometers per hour. So it's moving downstream at somewhere between 80 and 100 kilometers per hour, whereas it's moving upstream at 20 kilometers per hour. So within a short number of detector stations, then you lose that influence.
But that's still less than the free flow speed.
Yes, because they're getting back up to their free flow speed. And then let's say you go 2 stations downstream, then pretty much everyone is back to their desired speed. You know, or I assume that based on what I see from prior speeds. Sure.
Of all the locations where you found bottleneck activation,
Yes.
were you able to figure out why some locations would have more activations? It seemed like most of the activations were occurring around B22.
Yes.
Is it because of, I mean, why were the trucks,
Yeah.
why did they decide to go to
There's so the question is why in particular these areas that had multiple activations, why were they being activated there? Is that kind of what you're getting at? And you know, we looked at things and again had to rely on my German colleagues for this. Was there like some big attraction there? Is there on certain days, is there a soccer stadium or something like that would have a bunch of people going there? And the answer really was no, there's not a particular reason why there'd be lots of people certain times of day that were wanting to make the exit. But I think that the idea that it is an uphill grade, about 3.5% grade, and that the trucks were moving more slowly than they had been moving when they got onto that grade, I think that was part of it. You also are just coming over a vertical curve, and the exit actually occurs just over the crest of the vertical curve. And Chris helped me out with some of the analyses of these as well. And what we determined is there wasn't a real sight distance issue, but the idea was that because the exit was just over the crest of the vertical curve, that people that were wanting to make that exit were probably pre-positioning themselves ahead of time. And so you had people moving over into that right lane maybe further in advance of the off-ramp than they would have been if it would have been flatter terrain. It wouldn't have been kind of lying over the crest of that curve. So some of these things become, some things the data I was able to extract, and then other things it's somewhat my subjective opinion as well. You try to be as objective as you can, but you also know that driver behavior is a little bit funny thing to pinpoint sometimes. So I think it goes back to the question about whether the European drivers have any basic differences, and I believe that they're actually a little bit more rule-oriented that way. They do move over. When it says trucks use right lane and start, particularly when there's a sign, I think they do tend to follow that a little more. I also think that when you see the sign that says Friedberg exit now, then a bunch of people move over now. Maybe on I-5, people are a little more daring and make that last-minute lane change over to make the exit, but I don't think that was occurring as much in Germany.
I was just curious if you looked at the southbound direction, like the AMC coming into Frankfurt, and looked at any of the...
Not in detail, and it sounds like a pathetic answer, but I actually didn't have access to that particular data because I was dealing with long distance. It wasn't necessarily the easiest thing to just get more data on women. So the majority of the data that had been archived and then had been preliminary processed was all for the northbound. Yes?
What seems interesting is that when the shockwave heads back, it doesn't make any larger impacts when it hits the other bottleneck.
Yes.
And it stays in the thin line.
Yes. The question is noting the incidence that red line that we saw moving back moves right through those interchanges and doesn't seem to spread or anything as it goes through. Yeah, I found that to be very interesting. And that's what's interesting is that there were some cases when there would also be then a bottleneck that would occur simultaneously at the at the upstream station, but that I could analyze that and I could see exactly what was causing that one. So sometimes they would join and they would combine, but oftentimes you could see them moving right back through the stations with very little spread, which means that basically what's happening is that you've got the bottleneck that's activated, and then that shock is moving upstream, and let's say the period of congestion was say 12 minutes, like on that first one. It was congested at each station for about that same 12 minutes, and it seemed to be able to flush through at the, without any noticeable effect, whether it was at an isolated station or whether it was at an interchange.
So you mentioned that before the bottleneck activation, the traffic condition can be characterized as unrestricted flow.
Right.
But looking at the speed curves that you show, the speed seems to be pretty low. It was around 90 kilometers per hour. So that doesn't really strike me as uncongested.
It was, I think, and the question, I'll repeat the question, is talking about the speeds prior to the activation of the bottleneck. And Sue was questioning whether that 90 kilometer or so per hour speed was still in a free flow situation. It's certainly not, what we'd call level of service A, not the only vehicle on the road. So they're certainly not traveling at truly free flow speed, but they were moving. In other words, there wasn't excess accumulation between those stations at that point. So all the vehicles were moving through at that speed. And then what you're looking for, of course, the 90, it's interesting, just a straight speed threshold, I think there's a danger in using just a speed threshold as saying this is activated and not activated, because other times the 90 could have been a drop from some much higher sustained speed. So it's when the flow is dropping that you're really looking at that activation point. I think a strict speed threshold, while an interesting one to look at, you shouldn't get. I tried not to get too caught up with just raw magnitude of speed, but instead changes in magnitude and those notable changes in when they occurred. Does that answer the question?
Any other questions for Roger? Well, before we thank Roger one more time, just a reminder that next week Portland City Commissioner Sam Adams will be here to speak about paving streets, stormwater, green streets. So see you then, and thanks a lot, Roger.
All right, thank you. Thanks.